Hey everybody. So let me go over just a few more examples of using this whole conservation of energy method, just so you can see how it works. So here's a kind of classical physics problem, is this kind of loop-de-loop. So let's say you have a mass here, and this is a smooth ramp. How high does it have to be here to make it around the loop-de-loop? So this is some radius r. So as this mass goes around the loop, I'm kind of zoom in on it. Like it's here, and then it's over here, and then it's up at the top, and then over here, and then it comes back. So notice that no matter what, the weight is down. But the normal force is normal to the loop, so the normal force. And if you go, like if you start really high, then it goes really fast, then there's a lot of normal force. But let's find the minimum height necessary to just barely make it kind of through the loop. So then as n here approaches 0, this one, as n approaches 0. So that's like barely enough to keep it on the track, basically. So the free body diagram here, there's weight, and then there's normal force that we're kind of making it go to 0. So I'm just going to ignore it at this point. And let's pick coordinates however we want. Let's say like this. Right, so some forces in x is only that one, equals mass times acceleration. But notice that it's going in a circle. So the acceleration is centripetal. This is centripetal, meaning v squared over r. So then we have mg equals mv squared over r. This mass cancels. So we have kind of this constraint. Like it has to be going this fast to not fall off of the loop-to-loop. Okay, so let's keep that in mind. It has to be going that fast. Now, for energy. Let's go here. Let's say initial, final. Okay, so what's the initial energy here? So let's start at rest. So the kinetic energy is 0. What about the gravitational potential energy? It depends. Depends where you pick the datum. Do you want to pick the datum here, 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 here? They're all good choices. So you just pick one and you're correct. So how about I'll pick here at the bottom of the loop, the datum. Okay, so based on my choice, the gravitational potential energy is that high. So the weight times the height above the datum, h. Okay, and there's no spring, so there's no spring potential energy. All right, now final, where final meaning at the top of the loop-to-loop, right here. Again, this is radius r, right? So how fast are we going here? We have to be going this fast. So what's the kinetic energy? 1/2 mv squared. What about the potential energy? We're this high above the datum. That's the diameter, right? So 2 times radius. So plus mg 2r. And that's it. Right? So now we have 2 equations. Let's plug this into this one. So let me rewrite this. V squared equals gr. That goes right there. Gr. Okay, and then mass cancels on both sides. It's non-zero. G is also non-zero. cancel, cancel. So H equals half and 2, so 2.5, 2.5 R. There we go. So we have to be at least, right, if this is R, that's 2R, that's 3R. So right around this over here, 2.5 R. That's how high it has to be to just barely make it around the loop. If you go even higher, then it just goes faster and you have more normal force up at the top. Okay, let's try another example. So how about, we need one with a spring in it, right? So let's say we have a block over here connected to a spring, and then there's a pulley, a massless pulley, and then there's another block connected by a string. Okay, and then let's say there's friction here. So we know the coefficient of kinetic friction, we know the spring constant. So let's say if we're given the two masses, the spring constant and the coefficient of kinetic friction. And let's say we release from rest, and then like block 1 goes over here, block 2 ends up down here, and let's say that distance is d. So let's say we know that as well. How fast are these blocks going? So what's the speed here? So they have different velocities, right? Because block 1 will have a velocity like this. Block 2 will have a velocity like this. Those are different vectors, right? Because they have different directions. But they'll have the same speed because they're connected by the same string. So what's the speed of the blocks? The speed. All right, let's try the whole energy method. So this is not true, right? Initial is not equal to final because there's friction right here. So there's work by a non-conservative force, friction, kind of messing up our energy conservation. So first, how much is this? So the block is going toward the right, so the friction force is opposing the motion this way, kinetic friction. So I'll draw the free body diagram. Okay, so that's the free body diagram for the block. I'll pick coordinates. Okay, so in the x direction, okay, and in the y direction, and the block is moving in the x direction. There's no motion at all vertically in the y direction, so there's definitely no acceleration. So that means n minus m1g equals 0, or n equals m1g. And we know that friction is mu times n. Let me make some space over here. Okay, we know that friction is mu k times n, the friction force. What is the work by friction? The friction force is to the left, the displacement is toward the right. So what is the work by friction? Work by friction, it will be this friction force vector dot this displacement vector, and they're just opposite direction. So if you take the dot product, it's like this magnitude times cosine of 180, so that's just minus this times this, and then that's it. And we just have the expression here, mu k times n, and we just solve for n right here, n equals m1g. N equals m1g. Okay, so look, we have an expression for the work by friction. It's that in joules. Okay, so that part's good. Here, let me write this up here. Okay, just so that we can look at the picture, and I'm going to write it over here. So work by friction, got it. It's right here. Minus mu k m1g times d. Okay, initial. How much energy initially? So for block 1, it's at rest, so the kinetic energy is 0. And I didn't say it, but let's say the spring is unstretched. Spring initially unstretched. Okay, so then if the spring is initially unstretched, then the potential energy for the spring is 0. Okay, what about potential energy, gravitational potential energy? Depends on the datum. So for block 1, what if I pick the datum here for block 1? Then it's at the datum, so the gravitational potential energy for this is 0. Okay, for block 2, I can pick a datum for block 2, a separate one. So we can either pick it here, or here, or here, it doesn't matter. So any of the choices is fine. So how about we go with here, datum, for block 2. So if the datum is here, we're now above the datum by this much. So for block 2, it has gravitational potential energy, m2g d, above the datum. Okay, and then that's it. Now, final. Block 1 is now here, going this fast. So it has kinetic energy, 1/2 mv squared. Okay, and now the spring is stretched by this much. So now the spring has potential energy, 1/2 k this much squared. It's stretched by d squared. Okay, what about the gravitational potential energy for block 1? It was here at the datum, and now it's here, still at the datum. So the gravitational potential energy for block 1 is still 0. Okay, let's go on to block 2. So block 2 was here at rest. Now it's here going this fast. So it has kinetic energy, 1/2 mv squared. And it was up here above the datum. Now it's here at the datum. So the gravitational potential energy is 0. And then that's it. Block 2 is not connected to a spring or anything. So here we go. We have this equation. We were given all of these. So the only unknown is this. All right, so just solve for the speed. That's the only one unknown, and then that's it. Okay, so keep practicing. If you'd like to see more examples, just let me know, and then I can post more videos. So I'll see you on the next one.